Aloha class, we are in chapter 4. Check it. Buckets. All right, section 4.1, extreme values of functions. With respect to the AP exam, we're on topic 5.2, which is our second. Remember, we learned the intermediate value theorem. Now we're going to focus on the extreme value theorem, and we're going to focus on local extrema and critical points. All right, we have our enduring understanding, our learning objective, and our essential knowledge. Hit that pause button if you want to check those bad boys out. But here we go. 4.1, extreme value of functions. So what's cool about this lesson is we kind of do chapter 3, where we just get really good at finding the derivative of stuff. And now we use how do we use it? You know, what are applications of that? And that's what we get into here with chapter 4. And it's pretty much the entire of chapter 4, okay? But here we go. It says discuss homework after your 3B test with your classmate. We'll get into that. That will be a little bit familiar when we look at it. But we start with the definition of absolute extrema. And you did this stuff in pre-calc, both of these two things right here, okay? But definition of an absolute extrema, the biggest or smallest, important here, y value in the interval. Let f be defined on an interval I containing c. F of c is a minimum on f if f of c is less than f of x for every single x value. F of c is a maximum on that interval if f of c is greater than f of x, those are y values, right, for all of the x in that given interval, okay? Definition of a relative extrema. If there is an open interval containing c on which f of c is a maximum, so we're saying it's a maximum, then f of c is called a relative maximum. If there is an open interval containing c on which f of c is a minimum, then f of c is a relative minimum. We want to be very good at using the calculus language, okay, class? Basically, relative extrema exists when the value of the function is larger or smaller than all of the other function values relatively close to that value. How close is relatively close? So let's look at this. Okay, and it's kind of this whole first couple pages, you guys, is definitions, terminology, etc., etc. Example 1, determine whether each statement is true or false. For each false answer, provide a counterexample. Okay, whenever something's false, we want to give a counterexample. Hit pause, answer A, B, and C really quickly. Okay, A, every function must have an absolute max. B, every function must have an absolute min. No, 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 because I could have a function that looks like that goes on forever, and there would not be an absolute max or absolute min. Okay? C, there is a way to guarantee a function has an absolute max and absolute min. Believe it or not, that is, let's go ahead, false, false, but this guy's true. What I could do is I could use that same function, but let's cut it off. Let's start it there, and let's end it there. So even though that goes on forever, let's say I limit it to the interval from A to B. And if I limit it to an interval from A to B, A would be an absolute minimum, B would be an absolute maximum, or I should say f of A, right, would be the absolute minimum, f of B would be the absolute maximum, okay? Here we go, the extreme value theorem. I told you there were 3 main theorems we learned in AP Calculus. This is number 2. If f is a function and it's continuous on the closed interval, closed, okay, then f has both a min and a max. Okay, so in this situation right up here, that's pretty much the extreme value theorem. If I have a closed interval and I'm closing that bad boy off, and f is a continuous function, which means it's not going to jump, not going to be discontinuous, anything like that, then there has to be a min and there has to be a max. Guaranteed, kind of like my jumper, okay? Example 1, let's kind of show what this is all talking about. Okay, the function f of x is shown below. Okay, it's that bad boy right there. Find the absolute extrema of a function on each given interval. If you don't have a max or min, which part of the extreme value theorem hypothesis is not satisfied? Okay, let's look at -4 to 0. Ooh, we're including both of those bad boys? Okay, so let's check what's being satisfied. Okay, f of x is continuous. Check, right? There was no pointy place, right? There was no discontinuity, right? We're good to go. I said pointy place. We're not doing differentiability, right, class? Just handling continuity. Okay, next is the interval closed. Is the interval closed? Check. That's what those brackets mean, right? And then guess what? If those two things are satisfied, and those are the only two things I need in the hypothesis of the EVT, then that means I have to have a max or min. Do I, class? Heck yeah, I do. F of -4 is an absolute minimum, right? And it occurs at x equals -4. The value is 0. F of 0 is an absolute max. And let's look at f of 0. So that means at x equals 0, there's an absolute max, and its value is 2. It's very important to make sure you say that right. Okay, look at B. Hit pause. Try your best. Okay, here we go. Let's graph this guy. Now I'm going to go from -2 to 0. Oh, snap. Why didn't anybody? Yuck. That should have been like that. And I am not rewinding, but you guys fix it. So that means there was an absolute max at, there's absolute min at both. So both of these guys, hopefully you're saying, Mr. Tanaka, what are you talking about? We have 2 absolute minimums, right? We're guaranteed 1. And I have an absolute max right there at that bad boy, right? And the absolute max would be, let's go ahead and fix this, f of -2 is our absolute max. It happens at x equals -2, and its value is 2. Okay? Better look at that graph when I try to draw these bad boys. All right, I'm going to erase this so we don't get a little bit confused with my little boo-boo. All right, let's graph this guy from -2 to 0. See, I'm looking here now, so I'm just talking about that piece. So I'm going to make sure I draw that correctly. Oh, snap. Open circle, closed circle. Okay, so for B, f of x is continuous. Is that good? Check, right? I didn't have to lift up my pencil. Okay, is the interval closed? No way, Jose, that's that open circle right there. So then that means I can't use the EVT. But guess what? There happens to be an absolute max. The absolute max is at f of -2, right? That's an absolute max. But guess what? It didn't care. Only if the continuity and closed interval are satisfied are you going to have both a min or max. So for this one, I happen to have a max, but I didn't have a min. Why? That interval wasn't closed. Okay, let's keep rolling. All right, I want to keep my picture there so I don't draw the picture inaccurately. So let's take a look at this from, oh snap, if I'm really good, I already noticed there's a big issue going on here. 2 open circles? What you talking about, right? Here we go. F of x is continuous. Check. I'm halfway there. Interval closed. No way. What? No way, Jose. All right. So guess what? I don't have a max or a min. And some people are going to be saying, yeah, you do, Mr. Tanaka. Okay, you tell me tomorrow before school, I'll give you any candy you want. Okay, you have at it. But that doesn't have an absolute max. It doesn't have an absolute min. It's got none of it. Okay? All right, let's keep on rolling, class. All right, recall the picture to the right in the homework. I hope we had time to do this. If we didn't, here we go. Let's define all of these things, okay? What's A? Remember, that would be a minimum. Well, shame on me, right? This dude is definitely continuous, and it's definitely a closed interval, right? So let's go ahead and look. Let's just talk about these guys. We did it before, but that would be a relative. Ooh, that looks like it's going to be an absolute min. That would be a max. That would be a min. That would be a max, and that would be a min. And then I would just have to find these values to find which of those would be relative mins and maxes and which of those would be absolute mins and maxes. Okay, class, here we go. All extrema, whether it's relative or absolute, occur at endpoints or where the derivative was 0 or undefined, right? I had some zero derivatives there, horizontal tangents. I had a little corner cusp going on right there, and that was a max. Okay, we usually list these values as a candidates list, and then we determine which of them are relative, which of them are absolute. Okay, definition of a critical point, right? We've already used that term quite a bit here in AP Calculus, but let F be defined at C. If F prime of C equals 0, or if F prime is undefined at C, then C is considered a critical point. It's very important. Just because the derivative is equal to 0 or undefined does not mean there is a relative max or min there. Relative extrema can only occur at critical points, and critical points occur only when the derivative is either 0 or undefined. However, it is possible for the derivative to equal 0 and there be no extrema there. What the heck? F prime of 0 equals, well, I should first find f prime of x, 3x squared. So f prime of 0 would be 0, right, class? G prime of x would be equal to 1/3 x to the negative 2/3. G prime of 0 would be 1/3 times 0 to the 2/3, 1/0, undefined. So those are both critical points. Okay, and the question is asking, is there a max or a min at these values? Now, hopefully we know that the x to the third graph looks like this. No max, no min. The cube root of x graph, we should know what that guy looks like too. That's the inverse. It looks like that. Both of those do not have maxes or mins. So why do we do example 3? It teaches you. Some students think that because you get a derivative that's 0, like we did here in F, or a derivative that gives me a D and E, those are critical points. I have to have extrema. No, you don't, right? We just showed you right there, okay? Is there a max or min at any value on the domain? How do you know? No, because there are no maxes or mins at the critical points, and we are dealing with a domain of all real numbers. So we don't have endpoints. And what did this thing say up here? Right? Let's go all the way back there. You have to have endpoints or you have to have critical points to have extrema. Got it, class? I think you got it. I think we're rolling a little bit. Let's keep going. Okay. Example 4. Let's fill in some blanks. The critical numbers or critical points are, and this is very important not to get mixed up, are x values, while the maxes and mins of the functions are y values. In other words, if the point 2, 70 is identified as a relative min, the minimum of the function is 70, and it occurs at 2. This is how we correctly describe extrema. And you have to be good with that. So practice with your language, as you're going through these problems. Okay, class? Now let's go ahead and look at an example. Okay? And how we do this. Well, it says to find the extrema. Oh, sweet, sweet, sweet. We've got some endpoints going on there. And it says use your calculator to investigate first. Now that's what you need to do on your own. Okay? If you were to graph that bad boy, what would it look like? And I kind of have it here in my notes. But you would get a little something that looked like that. Oh, snap. Shame on me. We're going to start at negative 10, and we're going to go all the way until, what is it? Ooh, I'm going to stop right there. Okay, at negative 1. And if you look very carefully, ooh, I don't have an eraser, but let's pretend the rest of that stuff isn't there. Okay, let's go booyah, booyah, go away. Okay, so we're just the red graph, and I have endpoints, which means if it's continuous, that I will have I am guaranteed a min or max. Right, class? And so here we go. And I got like a little cuspy thing going on right there. So that's probably going to be a critical point. That means the derivative is 0 or D and E. And if it's a cusp, it's probably D and E. All right, so let's go ahead. And what do I do from here? Well, if I have endpoints, I want to consider those, right? That's number 1. You have endpoints. Where are your endpoints? My endpoints occur at, I guess we'll just say x equals negative 2 and negative 1. Okay, so I'm going to have to consider those bad boys. 2, as I got to find CPs, that's not Chris Paul money buckets. That is critical points. Okay, now how do I find critical points? Well, it said earlier that it's when your derivative is 0 or your derivative is D and E. So let's go ahead and find the derivative of g of x. Little chain rule. I think that's 2/3. Is it 2/3? Yes, it is. 2/3. Don't you dare touch the inside. Subtract that 1 and then multiply it by the derivative of x plus 2, which is 1. Let's simplify that. 2/3 x plus 2 to the negative 1/3. And if I want to know when that is 0 or when that is D and E, I'm going to set that equal to 0. Okay? Or D and E. And if I set it equal to 0, I get 2/3 x plus 2 to the negative 1/3 is equal to 0. And guess what? That negative exponent means it's in the bottom. And so I just want to know when a fraction is 0 on the top or bottom. Because if it's 0 on the top, it's 0. If it's 0 on the bottom, it's undefined. Well, here I get a little something of x plus 2 is equal to 0. X equals negative 2. That's going to give me a 0 in the denominator. That's a D and E. So always make sure that you check when your derivative is 0 and when your derivative is equal to D and E. So the way I like to do these problems is after you do step 1, locate your endpoint. Step 2, find your critical points. Step 3 is you check these bad boys, your endpoints and your critical points. And the best way to do it is make a table of values, g of x. Okay, and what were my endpoints? Negative 2. 10 and negative 1. And what's in between those was my critical point of a negative 2. And then guess what you do? This is where the biggest mistake is going to be made, class. You plug each one of those values into the original. Okay, now I did that, and you should make sure you do it on your own. Okay, you plug a negative 10 into that original right there. You end up getting negative 2 to the 2/3. We've done this in class. The cube root of that's negative 2. That'd be 4. Right, class? You plug a negative 2 up there in the original, you get 0 to the 2/3, which is 0. You plug a negative 1 in there, you get 1 to the 2/3, and you get 1. And guess what? The best thing about that is it answers all my questions. Okay, class? And so we're going to go a little therefore. I'm running out of space, so I apologize. Therefore. Okay, let's take a look at this thing. What is the smallest value there? It's 0. So therefore, g of negative 2 is an absolute minimum. G of negative 10 is an absolute maximum, right, class? And then we have G of negative 1 is a relative maximum, right? And it's easy to tell. That's the smallest guy. That guy is a min. And you know what I like to do after I do this is just to draw those guys, right? You have negative 10, comma 4. You have negative 2, comma 0. And you have negative 1, comma 1. And just draw it. Just draw it. Boom. Just connect the dots. And it's easy. That's the absolute max. That's the absolute min. That's a relative max. Relative to everything around it, that dude's a maximum. Okay? All right, hopefully that was okay. If it was not, hit pause. All right, we only did one example. So what you need to do right now, if you want to be really successful in AP Calc, is you need to go and do some worksheet problems right now, even before we go on to optimization. Okay? Now, why do we do optimization? Aloha class, section 4.4, optimization. We do this with 4.1. Okay? Because 4.1 is finding an extrema of a function. And optimization means we're trying to optimize something, whether we're trying to find the biggest of something or the smallest of something. So we have all these steps. These are kind of all technical steps. I'm going to kind of go through it with a problem, okay, rather than just look at all those steps, okay? Example 6. Kind of what you first want to do when you're given a problem is, what the heck is it asking? I got some rectangle. I got a semicircle, which you better be able to draw that. And you better be able to draw what this problem is talking about. Okay, so that's my step 1. That's my formal. Just draw it, know what it's talking about. What are you trying to find? We're trying to maximize that area there, make sure it makes some sense. Okay, that's it. Draw it, make sure you can draw that bad boy. What is step 2 in my book? Well, it's going to relate to geometry some way, somehow. So if I look at this picture here, that does relate to geometry. What are we trying to do? We're trying to find the biggest area. We're also trying to find the dimensions of that rectangle. So what the heck does that mean in geometry days, right? That means the area is equal to length times the width, right? That's what we're trying to find. Now let's relate it to the problem that we're doing, okay? We want the area, and I'm going to write it in function notation because that helps us out. But I want, let's see, the length. What the heck is the length and the width of this thing? Well, let's check this bad boy out. That, we don't know what it is, but that's x. Well, if that is x, guess what that is, class? That's x. So what is the length put together? That is 2x. Okay. Well, then what the heck is the width if I'm going to consider this to be the width? Oh, that's easy. That's a y. Okay, but that is not easy. Why is that not easy? Because I have x's and y's, and that makes, you're going to have to do implicit differentiation, right? Because we're going to try to optimize this guy. We have to find critical points, right, class? So that could take forever. So let's go ahead and let's see if we can get these guys written in terms of a single variable. Well, y, what the heck is y? How could I write that in terms of x? Oh, booyah! It's right there, which is 25 minus x squared to the 1/2. So there is the function that I want to work with. Well, then what the heck is step 3? We're trying to maximize this bad boy, so I need to know endpoints. It kind of looks like we're dealing from 0 to 5, right, class? And I also want to know critical points. Okay, so in terms of the x, we're going from 0 to 5, right? That domain was kind of determined, right, class, by the picture that I drew, and we have a square root. And then we also want to know critical points. Well, how the heck do I find critical points? Well, in order to find critical points, I need to know when the derivative is equal to 0 or DNE. So in order to do that, let's go ahead and find the derivative. Sweet! Product rule. 2x times the derivative of v, which would be 1/2. Don't you dare touch the inside, but then you better take the derivative of the inside. Plus, because it is a product rule, v, we're not touching that whatsoever in the product rule, and we're going to multiply it by the derivative of u, which would be 2. Now let's clean this bad boy up before we do work. Ooh, I get a negative 2x squared times the quantity, 25 minus x squared to the negative 1/2 plus 2 times 25 minus x squared to the 1/2. Okay, now that just looks nasty. And I need to know when the derivative is 0 or DNE. So what we're going to do is we're going to factor, right? Because we're going to end up using the zero factor property. And then able to do that, I have to have factors. And this plus right here is messing it up. It's turning it into 2 terms that I have to deal with. Okay, now whenever we factor in AP Calc, it's also always helpful if you just worry about variables. Okay, for example, there's an x squared here, but there's no x there, and there's a 2, but just leave it. Okay, just leave it. Okay, if not, it's going to cause trouble. But there is a quantity that is common, and it is that. So which one do I take out? What you've been doing in your entire life is you always take out the smaller. So what's smaller, negative 1/2 or positive 1/2? Duh. Negative 1/2, right? So I'm going to factor that bad boy out. And if you remember, when you factor out what happens, I'm going to factor that out of all this, so it all goes away, and I end up with negative 2x squared. But what the heck happens if I factor a negative 1/2 out of a positive 1/2? We'll go old school. We'll practice it in class, but it's 1/2 minus a negative 1/2. And what the heck is 1/2 minus a negative 1/2? That is uno, ichi. 1, okay, plus 2, and then we get 25 minus x squared to the first power. Well, guess what? I can clean that up even a little bit more. Let's be real right now. These problems are so fun because they take so long. Okay, and then we got that guy. And then what's left here? Negative 2x squared plus 50 minus 2x squared. Collect some like terms, and we get a prime of x is equal to 25 minus x squared to the negative 1/2 and negative 4x squared plus 50. Okay, so you can, I know some people like to rewrite these. You know, I like to save some time. What step did we call that? We called that 3, my step 3. It's a little bit quicker than going all there. So we're going to go 4, and we're going to find out when the derivative is equal to 0. And we want to find out when the derivative is a DNE. Okay, and we want to find out when the derivative is a DNE. Well, when the heck is something equal to 0? Now, if you look, you can rewrite it. You do not have to rewrite it. But if you feel like it would help you out, you rewrite it. And you rewrite, if it's a negative exponent, you put it where it's supposed to go. But right, that derivative is going to be equal to 0 whenever the numerator is equal to 0. You don't technically have to rewrite it to be able to do that. But if I just care when the numerator is 0, who cares about the bottom? Leave it out. Okay, and I'm going to solve this. Negative 4x squared equals negative 50. You get x squared equals 50 over 4, which is 25 over 2. Use square root, which is plus or minus the square root of 12.5, right? Who cares about the negative, right? Because you can't have a negative distance in this real-life application problem. Okay, let's do the DNE. Well, the DNE, all we care about is when the bottom, and we don't even bring that 1/2 with it, because if 25 minus x squared is 0, the whole thing is 0. And if we solve that bad boy, we get plus or minus 5, right? Who cares about that guy? All right, that's step 4. All right, step 5, let's go ahead and test these bad boys. Okay, let's test these. So how do we test these? Remember, we're going to test the domain, the endpoints. It's got to be closed off, right? So we're going to check 0 and 5, which is interesting, right? 5 was in the domain. That was the endpoint. But 5 also ended up being a critical point. Right? And then we also got the square root of 12.5. So remember, how do I get these answers right here? You plug all of these guys into the original. And I can't even see my original anymore. So what I am going to do is go off my notes and save some time. But a of 0, I get 0. A of the square root of 12.5, which was a critical point, we get 25. And a of 5, I get 0. And those are just plugging those values, remember, into the original. Therefore, the dimensions of this rectangle are, remember, my length, if going back up to those notes, was 2x. So it'd be 2 square root 12.5, right, class? By my width was my y value. So if I plug that back into the original, I get the square root of 12.5. And the actual area would be multiplying those two bad boys together, which would be 25. And I don't think they gave me units, which it would be units squared. That is section 4. Try some of those practice problems right now so you get better and better at optimization. We spend a good amount of time flipping the classroom and practicing those in class. If you want to get great at it before class so you win a game and make some buckets, make sure you come in for some help in the mornings. Aloha, have a great day. Watch your Aloha Friday videos.